Welcome back, everybody. My name is Dennis Wall, and I'm moderating this session today. Welcome back, everybody. This session is on deep neural networks for neurosciences and psychiatry. And it's a particularly exciting one, given the time and given the importance, the rising importance of artificial intelligence in medicine. And I am pleased to be joined by two fantastic colleagues, Trevor Cohen and Gaith Haboob, who will give talks. Before they start, I'll just try to set the stage, just by sort of remarking on the importance of the Renaissance in AI, which has really been largely driven by the successful application of deep learning. And many in the audience probably now know and understand and appreciate what deep learning is. This is really an aspect of artificial intelligence that involves training an artificial neural network with many layers. That is, the layers they're representing a deep neural network on increasingly large data sets that are becoming more and more accessible. A lot of the success has been driven by image classification tasks, but the recent confluence of large-scale annotated clinical data, like the ones you've been hearing about in this AI Med Clinicians series, as well as advancements and increasing successes in machine learning methods, open source machine learning packages, affordable, rapidly growing computational power and cloud storage, and things like that has fueled the exponential growth in AI. And this really gives way to the promise of a changing landscape in medical practice in the near term, which I'm particularly excited about. AI systems already have been deployed and are being used in practice today for diagnostic tasks, for prognostic tasks, for example, in non-small cell lung cancer and breast cancer, and obviously now can be very important in assisting surgical interventions. So we see things happening in AI in radiology, cardiology, pathology, dermatology, and now increasingly in neurosciences and psychiatry. And that's going to be the focus for today. Where are these successes starting to emerge in the applications of artificial intelligence, broadly defined, including deep learning, but not necessarily exclusive to it, in the fields of neuroscience and psychiatry. So I'm particularly excited about this session. And I think I'll start. I think Trevor will go first, right, Trevor? And
yes.
And then we'll have, are you guys there? Okay, good. And Gaith will go second. I'll start by introducing Trevor, and then when he completes, I'll introduce Gaith. But let me begin by introducing Trevor. He's an amazing individual. He's a fellow of the American College of Medical Informatics. He's professor in biomedical informatics and medical education at the University of Washington. And his research is focusing on the development and application of methods of distributional semantics. And more broadly, he's interested in this concept of clinical cognition, which I love, the thought process through which physicians interpret clinical findings and ways to facilitate these processes using automated methods. And so I'm excited to introduce Trevor, and he will discuss issues about large language models, linguistic anomalies, and Alzheimer's disease dementia. Take it away, Trevor.
Right. Thanks very much for that introduction. So
pleasure. Yeah.
I will share my screen. Right. So as Dennis mentioned, I'll be talking today about large language models and their implications for diagnostics in Alzheimer's disease. And so these large language models sort of segue from the things that Dennis was discussing in the introduction about deep learning models. So language models are models that learn to predict text in large unlabeled corpora. So we can use, in an unsupervised setting, a large amount of text, train the models to predict held out aspects of that text, like words or sentences. And then the models through that acquire information about patterns of language that they can then apply to other tasks. So they can transfer this in what's called transfer learning, and then do well in smaller data sets by bringing this knowledge from a much larger unsupervised set to bear. So there are a number of such models. They've had a huge influence in recent years on natural language processing and computational linguistics, improving performance across a broad range of tasks. I've listed some of them in the slide, just to give you an idea of the sorts of predictions they learn to make. This is some output from GPT-2, which is a model from OpenAI, and I've given it some cues and asked it to complete the sentence. And you can see that what it does is come up with sensible conclusions to these sentences that sort of predict how a human might complete them. You can also see in the image what the model's paying attention to as it completes the sentence. Like, for example, here it's looking at London and capital and united to predict the next word, kingdom. One of the things I wanted to draw your attention to about these models is that they're large, hence the title. So they have many, many millions or even billions of trainable parameters. And this is interesting to consider in the context of neurodegenerative disease, where the data sets we have to work with are much smaller than this. So many, many orders of magnitude fewer data points than we have parameters. The main idea of this talk is as follows. So we have these large language models. They've improved performance across a range of NLP tasks. They learn statistical regularities from typical language. And perhaps we can flip that around and use them instead to detect anomalous language that occurs in the context of different pathologies. But the problem that I'd like to draw your attention to is, well, how do we know that the irregularities that these models are picking up on are irregularities that are diagnostically important when we have so many parameters that we unleash to train models to distinguish between small samples of participants? So for this talk, I'm going to focus on the application domain of Alzheimer's disease, which, as we all know, is highly prevalent. There are consequences to delayed diagnoses. There's an opportunity to disseminate techniques to come to diagnoses earlier that are driven by deep learning models. And so one of the reasons this is an appealing area to people like me who are interested in computational models of language is that there are data sets available. So one of the ways in which language is elicited from people with Alzheimer's in order to make diagnoses is using cognitive tasks, such as the picture description task. And I'm showing you on the right panel an example of a picture description task where a participant might be asked to describe this picture. There are data sets available that have responses to this task from people with and without Alzheimer's disease, and they've spurred research on the development of automated methods to come to diagnoses. And these have progressed in a typical pattern from feature engineering, where people would try to develop features that are useful manually, to deep learning models that can identify the features through training. So where we entered this picture was at the point where the best performing model using text on this data set, Dementia Bank, that I introduced in the previous slide, was using something called language model perplexity, which you can loosely think of as how surprised the language model is by language it sees. So if you train it on normal text, this gives a measure of how surprised it is by anomalous text it might encounter. And the best performing model at that time was a model that built two language models, one trained on people with dementia and the other on healthy controls. And so the idea was, well, if you took the difference between how surprised each of these language models were by a transcript, this would give you an indication of which group it came from, because the healthy control model should be more perplexed by an abnormal transcript. The Alzheimer's disease model should be less perplexed by that. And if you raise the roof and drop the floor in that way, you'd have a large number that you can then use to make a prediction. And this turned out to be a very effective approach with impressive performance on the Dementia Bank set, an area under the receiver operating characteristic curve of 0.92, which compares favorably, or at least is at the top of the range of assessments of the performance of a range of neuropsychological tests that are more difficult to administer than the cookie theft task. But what could go wrong here is that the Dementia Bank set is not matched for age or education, so we can't be sure that the model is actually picking up on signs of Alzheimer's disease. It might just be classifying people by age or by education. And so we wanted to look more deeply into this and developed two techniques to investigate what the model might be responding to. The first we called interrogation by perturbation. It's illustrated on the left, and it involves using transcripts that have been deliberately changed to simulate the progression of disease in Alzheimer's disease by replacing more specific terms with less specific terms, or less frequently occurring terms with more frequently occurring terms, to simulate the loss of access to specific terms that occurs as Alzheimer's disease progresses. And the second approach we called interrogation by interpolation. It's a bit more straightforward. If you think of these models just as collections of parameters, you can average them and look to see if there's a sort of dose effect of the dementia model as its contribution is increased. So these are the results in brief that we got trying these approaches. And if you look here, you can see with the perturbation approach, we see that the control model, which is shown in blue, is more perplexed by transcripts that simulate severe dementia, which are towards the right of the graph. Whereas the dementia model is more perplexed by transcripts simulating healthy participants. And we found this quite encouraging in that it gave us confidence that the models were in fact responding to a known linguistic change that occurs with Alzheimer's disease. With interpolation, we can see something similar where the transcript simulating, if we just look at the transcript simulating severe dementia in blue, as we increase the contribution of the dementia model, the perplexity decreases. So, although if you look over on the right, you can see it actually, when you get to the simulation of the most severe dementia, the model becomes more perplexed than we'd like it to be. And so we found that we could use the diluted model rather than the pure model and improve the performance of these models. The next work I'd like to discuss involves a more direct approach to dealing with this issue of age imbalance, which is just to balance the age of the people in the set. So there's a subset of Dementia Bank that's been released where it is age balanced, but it's of course a much smaller set. It was released in the context of a challenge evaluation. And we wanted to see if we could expand this set by introducing additional data gathered from the Wisconsin longitudinal study. And this gave us a much larger set of cookie theft transcripts, but what could go wrong here is that, well, people in Wisconsin may speak differently to people in Pittsburgh, where the address challenge set was collected. And so it's possible that models could pick up on linguistic differences between these populations. And if most people in Wisconsin in the set are healthy, it might just learn to predict that people in Wisconsin don't have Alzheimer's disease. So we found an approach to this in the deep learning literature on image processing, where they showed that what you can do is, if you have a potential confounding factor like the provenance of the data set, in our case, you can train a model to predict not only the outcome of interest, here healthy versus dementia, but also this secondary potential confounder, like as in our case, whether someone comes from Pittsburgh or Wisconsin. And that persuades the model to some degree not to use that in the prediction of the primary outcome. So when we tried this in the context of our set, we found that performance does indeed improve with these secondary objectives. And I should note here that these numbers are inflated compared to the numbers on the address challenge itself. And that's just a factor of the imbalance in the data set driving up the AUC, and the fact that if you say no a lot in the context of a data set where most people are healthy, your accuracy will be driven up. So they're not comparable to the challenge performance, but you can see an improvement with these auxiliary objectives. But maybe the more interesting thing is that the auxiliary objectives were almost perfect in their classification performance. So the model does a really good job of distinguishing between people from Wisconsin and from Pittsburgh. We're not entirely sure why. There's nothing as obvious as yinsing in the data set. So we need to do more work to figure out what's going on here. So just to conclude, hopefully on time, what I've tried to draw your attention to here today are large language models and their potential as diagnostic instruments, and some of the perils that might emerge when we have small amounts of training data present in the context of large models. And then I introduced two ways to approach this problem, the one involving probing tasks that deliberately look for known manifestations of a condition, and the other involving efforts to deconfound models by trying to persuade them not to use extraneous information in their prediction tasks. So with that, I'd like to briefly acknowledge my funding sources, collaborators, and information sources. And thank you for your attention, and hand the microphone back to Dennis soon.
Fantastic. That is really compelling information. And we'll hold questions to the end and give time for Dr. Gaith Haboob to speak. I'd like to just quickly introduce him. He's a neurosurgeon at the Cleveland Clinic, where he leads an effort on continuous improvement of artificial intelligence initiatives. He was born and raised in Syria before he finished his education in the USA, and this, I think, really heightened his awareness of the lack of resources and the need for alternatives. Where he's been applying a lot of his expertise in the field so far is in the areas of the judicious use of artificial intelligence in healthcare, which naturally can provide humanity with great substitutes to the costly healthcare system that exists today. So I'm excited to hear from Dr. Haboob and his perspectives on artificial intelligence in healthcare.
Well, thank you very much, Dr. Wall, for the generous introduction here. I'm just going to share my screen. And thank you all for having me as well. So my title for my talk today is Embedding and Moving Models to Production. And it's really a technical and clinical view. This is my disclosures. So really, I kind of identify two examples. One is, sorry, 1 second. Okay, one is on reliability and reproducibility in machine learning using a robot, use example here, and the other is on the security and performance model serving using clinical workflow, use example. So the way I think about a robotic system is basically a brain that connects some sort of inputs to outputs. So on the left side, you can see here an input is some sort of navigation and or computer vision that feeds into a brain, which in turns performs some sort of action. And in this situation here is screws placement in spine, as this, me, a spine surgeon. So sensor fusion is really combining multiple inputs to help understanding the surrounding environment. And these sensors can be manual from the operator or some sort of accelerometer, gyroscope, navigation system, ultrasound, tactile, and so forth. So why do you need even sensor fusion here? Basically, the robot, so we have here an example, which is basically a robot wants to travel a long distance. And when you're next basically to the navigation system, you're really certain where you are. And as you travel away, that certainty get worse from that reference point. So for example, here the robot thinks is 5 units of distance away, and is in reality is 4.8. And that uncertainty get worse as the distance get further. So it's nice to have another sensory point here. For example, if you have computer vision for the algorithm, like for example here you can see a tree, and the tree is a reference to is next to the 10 units distance, and then the algorithm will be a little bit more certain about the location. So if you want to do planning with artificial intelligence, and especially in the setting of multiple complex multi-input, you have to basically answer some difficult questions with all these sensor input. So using artificial intelligence sometimes help you achieve that solution. We know that there are 3 main types of artificial intelligence, and we're just going to talk a little bit about reinforcement learning here. So all started in 2016, AlphaGo won over the world champion Lee Sedol in the game of Go. And that's kind of pretty impressive, especially the potential actions space of the game is 10 to the power of 10 to the power 48. So it's kind of unmeasurable, basically. That's followed by several publications on reinforcement learning gaming. And it's really performed strongly to perform complex logic. So basically in reinforcement learning, you have an agent that wants to interact with the environment. And based on the information the agent gets from the environment to perform some sort of action. And that based on that action, it gets a reward, either positive reward or negative reward. As an example here is some of these interesting reinforcement learning simulation environments you can try use. Basically, and what's interesting about this one is both rackets basically trained with the same algorithms, or both competing on the combined score or combined reward. So what we did basically generated some sort of logic in my situation as how can we use reinforcement learning to help us in robotics, basically. So the idea here is you have some sort of a simulation environment where you can, a brain kind of basically practice some of the actuation here and get this optimal solution. And then we can export that simulation solution into a physical robot. And if you train the algorithm, it actually learns. You can see on the top of the graph, there's the cumulative reward over time. And what you can see here is the algorithm after 20,000 practice, basically, of actions, it's suboptimal. But as it trains more than 150 million actions, it started becoming reasonable. So that was kind of encouraging to me. But it was the question I always had in my mind is the problem with numerical solutions. So in robotics, we're trying to kind of find solution for each patient. So every time you train this algorithm, you get some sort of a variety of solution. And while a lot of the time the solution is very good, but sometimes you can get stuck into what we call local minimum as opposed to reach all the way down where you want to be. So to minimize the risk with numerical solution, you might want to readjust the design. So what kind of might defeat the topic of today is what you might want to is actually simplify solutions. So AI might be a very useful tool, and prototyping sometimes, it's a very difficult task. You have multiple sensory input. So you throw in a very complex algorithm that kind of appropriately find patterns. But you might then go back and say, well, can we simplify it and do some sort of a more analytical, deterministic kind of algorithm and see if we can reach some sort of a closed loop solution here? Having redundancy, maybe a couple of algorithms that kind of one support the other or both provide two solutions might help you kind of minimize that potential risk on getting stuck in local minimum and not able to, reach it all the way to a production level algorithm. The other component I want to look at is that kind of pipeline, looking at more from a quality control perspective. So similar to the logic identified with FDA kind of perspective. So what you'll notice is when you look at AI's algorithm in general, all of them fall into the class 3 category in the FDA approval, which would usually require a pre-market approval if there's no predicate, which is most of the time. And it's kind of that similar logic, how you kind of approve an algorithm is some lot. You want to implement that logic into your pipeline. And finally, you want to also have good metric to follow when you're in operation, in your operation. So one easy one is if the algorithm performing one action and favoring it over other actions and exploring. The other briefly I want to mention is on security and performance models using clinical workflow example. So a while ago, we had this, we created an algorithm to help us identify how we can select our population better to operate on. And we looked at different metrics. But that's great. But then what do we do now? How are we going to use it? And in reality, I mean, every artificial intelligence pipeline falls into a relatively similar pattern, which is basically you have some sort of data ingestion, some data preprocessing, and some model serving to use that data. But what you realize very fast is, okay, but how can I use it? How can I deploy that model and serve it while at the same time keep it secured, have a good performance, and no bottlenecks and reach the expectation? It's kind of for me, I went down, I kind of realized these are the 5 ways I can use my models. So the first 2 is basically, you can call the function directly. At the end of the day, all machine learning is a function a function at the end of the day. It's an optimized function, but based on numerical solution. But at the end of the day, it's a function. You can mathematically write it to some degree. But when you realize, well, in deep learning is a different story, but in simpler algorithm, I say a logistic regression is great. You can write it very easily, but you will expose yourself to the third party or whatever we want to implement these algorithms. So you might kind of step back, and you might also not reach the performance. Similar to if you have to do it using the PMML language, which is a standard language for models. The other way, you can put it behind an API, but we realize as well as the performance will be limited if you rely on only one server. The other way is more the standardized way, which is rely on some sort of orchestrator that can handle the scalability of your model, either locally or on the cloud. So this is a pipeline we developed for our sepsis initiative, the clinic. And you can see here the standards, MFlow, kubeflow, airflow. These are really the standards. Either you can use it locally on or in cloud services. And by doing this, you kind of keep all third party, the EMR companies away, and you kind of protect your own IPs, and it also sometimes protect patients' data as well. So kind of in summary, I want to kind of mention the role of regulation is key in machine learning because of the nature of it. Being a numerical optimization solution as opposed to analytical. And you want to kind of also, when you do any sort of deployment, kind of prevent any bottlenecking by using scalable platforms for both data preprocessing and model serving. And the last thing is also prevent your IP from third-party exposure by hiding behind an API. And thank you very much.
Thank you. That's super compelling. I really appreciate you talking about these important concepts. And I will, I guess, kick things off here by basically asking. We've got about 10 minutes or 13 minutes really for discussion, I think. And I'll follow the chat to make sure that I pay attention to the questions that are coming through. But a general question for both of you is, as you're thinking about these approaches, so it's broadly defined machine learning approaches, not necessarily deep learning approaches, and their applications in, let's say, early detection or in the assistance of, let's say, neurosurgical practices. What are the trust barriers that must be addressed? Just an open question to get things started.
I guess I can start. So really, whenever I look at one of the questions that, I'm interested to do some sort of analytical solution on, is my first question is always, what's the incidence? Because sometimes I get a lot of questions about, let's do this project. And you realize the incidence of that class, I guess if you want to go in a classification type approach, is like 1% or 0.5%. And then, then my second question is, do we have enough data to support that, finding enough information on that prediction? And if both are, achieved, and I can create an algorithm and so on, then it really depends on what I'm looking at. For example, working on now with sepsis, and when you have an incidence of 1.72%, I don't look at accuracy and ROC anymore. All I care about is looking at the precision and recall, like positive predictive value, and the sensitivity of the model, because it's so much easier to get fooled. And so really convincing myself with the numbers is first thing, and then really testing it into more in a simulate the real-time environment is the other way I try to validate and get trust from the algorithm, basically.
Very, very good.
Yeah,
Trevor, you want to comment?
Yeah, so just comment. So, maybe some other angles of trust to consider are trust of the physician in the prediction, right? Like at the point of care, not the person who built the model, but the person who's looking at the output. And that, that's kind of an interesting area, because there are questions around that, like, what do you show? Do you just show a prediction, which is a number, or do you try to give some insight into how the model got to its prediction? Or how confident the model was in its prediction? And there's some interesting work in imaging where they've tried to develop systems that are more collaborative, that allow physicians to use information beyond the prediction itself in interpreting how valid they think it is. For my work, another area that trust comes into play is in the availability of data. So for example, we have some work where we're looking at suicide risk prediction. And we'd like to look at non-traditional data sources like search logs, for example, or social media data. And there are a lot of issues that arise around whether or not people might be willing to share those data. So there have been some high profile, I would say controversial incidents in which people have tried to institute early warning systems without the explicit permission of the people using social media sources, for example. Whereas we're kind of interested in how this might work in the context of a therapeutic relationship where there's a more sort of trusted framework for monitoring of the data and reporting of risks. So I guess trust comes into play in both of those areas.
Those are great questions. So yeah, so in summary, I think maybe just summarizing a little bit what you said, not fixating so much on the standard statistical metrics like the area under the precision recall curve, but instead looking at precision, looking at rather positive and negative predictive values, and then creating some relationship with the clinician whereby they understand the confidence in the predictions. And I think that those are really important points. A question from the audience is from Dr. Anthony Chang, actually, who is excited about the reinforcement learning and difficult, and asks the question: any software that can help a clinician to do a deep learning project without having a data scientist to help with the project? Does anyone know of any software out there that can help a clinician to do a deep learning project without having access to a data scientist?
So, the best I can say if you have access to cloud services like AutoML provided by all of the cloud provided services, is probably the easiest way. And you only need to define if it's tabulated or like an imaging type of data. You don't even sometimes need to define the schema of the data, and and you just need to obviously define the label. And they usually now, at least Google Cloud and their most recent, they've been relying on deep learning for even their tabulated data as opposed to tree-based algorithms.
Yeah, that's right. And I'll say that increasingly the accessibility to models within systems like Keras and PyTorch is very high. Like in other words, they can be called very easily. You can write things very quickly in a Jupyter notebook and things like that. We're starting to teach that more and more, Anthony, in our Stanford classes.
Yeah, maybe I can just second that and say we've certainly had physicians in our clinical informatics fellowship who've learned to use these tools directly themselves and done deep learning models. And so.
Another question that I think is quite an important one that's coming from the audience is: will we need an FDA? Will we need the FDA to approve these prediction models? And how about the legal implications that we must be dealing with when we use these models? Sorry, I'm reading the chat. So I think, it's important you touched upon this, Gabe. Talk more about it.
So I had actually one of the courses. I love Udacity. I don't know if you guys are familiar with Stanford. I'm sure you are. And one of the courses there on the healthcare AI, they kind of go over the FDA approval process, which has really been helpful to me and kind of practicing it. And what I would say is the way we were working around FDA approval is by having it as an assisting tool as opposed to a complete automation. So like in radiology, okay, well, it'll make diagnostic or triage thing, but still at the end of the day, the radiologist will review the imaging. The same, well, this patient is great, but this one is not. But at the end of the day, we're making a decision. If you want bypass that and start doing automation, yes, you'll need the FDA approval. And unfortunately, if you need FDA approval, you have to go through all the usually class 3 pre-market approval and the whole process. And it's not easy. And but Yeah, that's what I have on this. Unfortunately, I wish it's easier.
Yeah, it's been a little while since I looked at this, but when last I looked, the FDA already had a proposal for an approval mechanism in place that wouldn't just approve the model, in the context of a trial, but there'd be a continuing approval process where the model would also have to be validated in the context of the environment in which it's applied.
Right.
Regulation can slow things down, but this does seem quite important to me because, as you saw from some of the examples in my talk, like there are a lot of reasons why a model might not perform as well in a new context as in the context it was originally trained. And so having some sort of mutually understood and accepted framework through which the performance of a model in its local context can continually be validated and monitored just seems like a good idea.
Yeah, and I think that that's going to help solve a lot of these legal issues. To answer your question, and I can comment quickly on the fact that the FDA has become quite sophisticated in its ability to work with AI, increasingly so. They're committed to it. They've got specific programs in place, and I think it's important to work with the FDA early and often if you're going to be bringing something to market. So just something to keep in mind. Look at their recent definitions of software as a medical device. We've got about less than 5 minutes to go. I think 4 minutes to go. A question that I wondered about as both of you were speaking, when you have, let's say, these reinforcement approaches in place, or when you're using lexical time series data to make predictions, you do have to be very careful about the input of the data and about what optimality criterion you're using to tune your models. And I wonder, to what extent, let's just take reinforcement learning as an example, where the purpose is for the agent to learn an optimal policy that can maximize the reward function or other user provided kind of reinforcement signal. How when you're dealing with the policy, how are you defining the policy in this context? And maybe this is too big of a question to ask. It's such an important one, however, because when you think of reinforcement learning and policy maximize the policy to maximize the reward function, the policy itself becomes really critical. Do you have an example of a good policy for reinforcement learning?
So, I'm trying to think. So, actor critic. I usually use some sort of variation actor critic type of variation for reinforcement learning from an algorithmic standpoint. For the policy, the generated policy itself. So, it depends really. We're looking at more a continuous type of policy or deterministic, like right, left, or some sort of degrees. What I can say, like about the parameter tuning, is a disaster. I think it's a really tough. And it's so many parameters up and down, and then you start and want to create a personalized or precision type of medicine, per patient, and then you have to optimize each one per each patient, and then it becomes really difficult task, these hyperparameter tuning and retrain across many times over and over.
Yeah, but maybe can I follow with a sort of meta comment?
Yes.
It's a story. I'll try to be brief, but I was talking some years back to a friend of mine who's a very accomplished chess player about AlphaGo and models that learn through reinforcement learning, and he made this observation that the models play differently. Whereas a human Go player might try to increase their lead, like maximize their lead, the AlphaGo model will try to retain a small advantage consistently to the end of the game. And I was wondering, in the context of robotic surgery, if any of those differences in the sorts of things a human surgeon might optimize and reinforcement learning might optimize come into play. And I guess I ask because an optimistic spin on this might be, if there's a collaborative system and they're both optimizing different objectives, they're more likely to get to a better place together than either component independently. So I wanted to throw that out there.
I think that's a really great comment. And I do think that that's a great way to try to end the session, actually, is to think about the promise of AI in medicine being more of a partnership rather than a replacement, where AI is working together with the clinician and they're separately, let's say, maximizing some different objective function, but together the incremental improvements are realized. on both the efficiency and the quality of the programs that they're working on, the clinical programs. So I just want to say thank you to our speakers. This was a very compelling session, and we are officially out of time. I look forward to seeing everybody, especially you two, in person at the next AI Med conference.
Thank you very
Thanks
much.
very much.